Okay, today we will discuss about the epsilon tensor as in the three-dimensional geometry. In the three-dimensional geometry, this epsilon tensor is noted as epsilon I j k, and its values are defined as like this: I j k is equals to 1 if the I j k permutation is even. For even permutation, and equals to 1 for ijk odd permutation, and equals to 0 for the rest of the cases. By this even and odd permutation, I mean, let's say for an example, epsilon 1 2 3 equals to epsilon 2 3 1 equals to epsilon 3 1 2 is equals to 1. Say here they follow the even permutation 1 2 3 and then 2 1 3 means cyclic, but for the random permutations, say 1 3 2, for 3 2 1 and 1 3 2 is equals to -1. And this for the rest of case, we have two or more indices repeated, two or more indices repeated, okay, which means I112, I223, epsilon 232, so they all will be equals to 0. And you can also take one more example, 111. Okay, next move to the tensor, Kruthkov tensor. Kruthkov's tensor. So this tensor is of the fourth rank tensor, is a fourth rank tensor, and is denoted as in pairs Lm and Nk. These are two pairs, and they are in fourth rank. Some properties of Kruthkov tensors are: first one, that ALM comma Nk is equals to minus of this, and one of the pair of this get reverse, means AML comma Nk, and same for the other pair also, ALM comma Nk is equals to minus of Lm comma Kn. And the last property, which is cyclic property of Kruthkov tensor, is that AL, M, and K, by fixing one of the indices, this first, and continuing this cyclic property for the rest of these indices, we will get this ALM, AL, N, K, M plus AL, K, M, N. Then this cyclic property, the addition of all Kruthkov tensor, is equals to 0. In terms of second order derivative of ALM and K, this Kruthkov tensor, we construct a new tensor BLK, which is equals to summation M comma N is equals to 1 2 3 for the fourth rank, curl square A L M and K, curl XM and curl XN, where BLK is a Kruthkov tensor. A notable thing for the Kruthkov tensor is that the derivative of this Kruthkov tensor, curl BLK over curl X to the K, for the summation K1 2 3 is equals to 0, and this is a very important property of the Kruthkov tensor. Next one is relative tensor. If the components of tensor AP1 P2 up to PR, this is a mixed tensor Q1 Q2 up to QS, transforms as by this equation A bar alpha 1, alpha 2 up to alpha r, and beta 1, beta 2 up to beta s equals to curl x over curl x bar w a p1 p2 up to pr q1 q2 up to qs curl x bar alpha 1 over curl x p1 curl x bar alpha 2 over curl x p2 and so on, curl x bar alpha r over curl x pr and curl x qs over curl x bar beta s. So here in this ap1 ap2 and q1 q2 this mixed tensor is called tensor of weight w. Okay, and then curl x over curl x bar is Jacobian of transformation. Now if w equals to 1, then this relative tensor is called tensor density, and if w is equals to 0, then this tensor will be called absolute tensor. Okay, next move on to the conjugate or reciprocal symmetry tensor. Reciprocal symmetry tensor. Let's say a covariant symmetric tensor of rank 2 aij, then it is a reciprocal tensor. Then its reciprocal tensor is denoted by aij, which is defined as, we also call this contravariant, cofactor of covariant aij in mod aij by mod of ij, where this not equals to 0, the determinant of this not equals to 0,